if Jacques cannot answer them, I'm sure David Swain will be able to do so. So let's start. So well, this part of the talk is entitled "Vaccination Against Avian Influenza: A Crucial Component of Sustainable Poultry Production," and I will try to explain why. So this first part addresses two topics. The first one, why, it's maybe redundant, but still I think it's good that we gather all the arguments. Why is vaccination crucial for sustainable poultry production in the future? And then, well, I will look at the effectiveness of vaccination from an epidemiological point of view, and then in particular related to transmission in this case. So if we look at the control of avian influenza, I think we're all really dissatisfied with how that is going. But I think if we look at it historically, the way we are controlling the infection, well, it has really made sense for a very long time, because I think up until a quarter of a century ago, outbreaks of highly pathogenic avian influenza were really rare. And they would always start with a low pathogenicity virus mutating into a high pathogenicity virus, as you're all probably all aware of. And also in that situation, before 2004, highly pathogenic avian influenza outbreaks in wild birds were, well, really very rare. If you look at the literature before 2004, at least, well, I was only able to find one in 1961 in turns in South Africa. So from that perspective, it's good that we have people from South Africa in the call. And I think actually the consensus was at that time that, well, the case fatality of this infection in wild birds was really too high to allow for efficient transmission among wild birds. Well, this virus would definitely result in a lot of loss of host fitness in these birds. So there was no way that they would they would be able to fly with it, let alone migrate with it. Because a really high pathogenic virus like this, it really needs a high density of hosts in order not to fade out before before it is transmitted to a next host, and that is obviously not the situation how most wild birds live. So the role of wild birds in the epidemiology was considered negligible up until 2004. And I think if we point that together, then because HPAI outbreaks are rare and only poultry served as a reservoir, stamping out infected farms is really, well, the best option of disease control, because if you have removed the infected birds, you have also eliminated the virus. So it's not that we are, or that we have been stupid in the way we are controlling this infection. It made sense. It made a lot of sense, I think, during a large part of the recent history, and that has changed. Well, at the point when in 1996, this new H5N1 virus emerged in China, and well, at first, because at that time China was not as open as it is now, so it was not seen there for the first time. But through outbreaks in Hong Kong in 1997, also the Western world got aware of this virus, and the rest of the world got aware of this virus. So this virus emerged there. It was not eliminated. And most likely that was because also at that time, of course, there was a lot of development going on in Asia with, well, poultry becoming a really important source of protein to people. Because, well, we all know that in developing worlds, the animal protein consumption increases considerable, and poultry being one of the cheapest, it increased also a lot. Back in where we live, where Jacques and I live, well, there's really the impression that the intensified and industrialized poultry production is actually responsible for many of the problems we have in disease spread, like avian influenza. I think there is quite a little evidence to corroborate that. I think it's much more likely that this virus emerged in systems in Southeast Asia, where you have, for example, ducks over the paddy fields, and from that transmitting the virus regularly to wild birds, and maybe the same happening in live bird markets in Asia. Also, because apparently this virus is now spreading a lot in duck-like wild bird types, and not so much in chickens alone. So it might have been more likely that it went from ducks to wild birds than from chickens. Well, notwithstanding that, I think nowadays we are in a situation where, because of this constant spillover of virus from domestic birds to wild birds, we're in a situation where several wild bird species can be infected with H5 virus without substantial loss of fitness. And this is actually something that has been seen, as the right part of this graph also is showing, from the end of 2004 and before. It really was not noticed. So the ecology of the infection has really changed dramatically. So we are now in a situation where the virus is spread across the globe, usually starting in a situation in the breeding grounds in northern Russia, in Siberia, where many of these water birds, they go and breed there. There they mix viruses. Then a new variant virus arises, as we've seen, and then as was nicely shown by this paper of Verhagen already many years ago, but this is happening now from year to year. The wild birds then bring these new variant viruses to, in our case, Europe, but also to other parts in Asia and Africa, and it also has been demonstrated in 1516 to North America, although the recent virus has emerged actually from Europe to North America. We now see a spread of these viruses across the world. Then when they enter, for example, in a country like the Netherlands, where Sjaak and I live, we have these huge aggregates of these birds in our lakes during winter, because we live in a delta where you have many of these water birds overwintering. You get virus amplification, and from that we have poultry getting exposed to the virus. Of course, it also results in immunity in wild birds, which then stops usually during the end of spring the exposure to poultry again. But then, of course, these birds fly back to the breeding grounds again, and this circle repeats itself. So now we are in a situation where, since 2005, wild birds spread the HPAI virus across the globe. And for example, in Europe, we had that from 2005 to 2008. And from 2014, actually, each year. By mutations and reassortment with low-path viruses, it gives rise to new virus clades and H5 subtypes regularly. And we also know that at least the viruses that we've seen during each of these falls, that they have been different. So it's actually new ones arising. So nowadays we are in a situation where this virus is constantly present in our global ecosystems, and we have seen many subtypes over each of these years. And now the situation in Europe, and maybe David can tell a little bit about the situation in North America now. If we look at these figures from 2016 on, whereas we've seen it from 2014, but from 2016 on, you see that that each year there have been new incursions, which kind of varied in their intensity too. So 2016-17 was really a dramatic year. Then we had a number of years, as you see here in the maps, which were quite mild. So there were incursions, but they did not take off as much. And since and the last 2 years were typically bad years in Europe, where now also I think we had thousands of outbreaks in poultry have been notified. So that means that actually why vaccination is crucial, is a crucial component to poultry is kind of summarized here. We've seen that the ecology of the virus has changed considerably. The virus is now endemic to wild water birds. Outbreaks of the disease among poultry occur frequently, as they were really rare. And it also means that, well, we of course stamp out infected farms, and well, we should do, because of course these birds will suffer enormously from the infection. But this stamping out does not eliminate the virus anymore, because it still continues to be present in the ecosystem. Also, from a consumer point of view and from a citizen point of view, it's the current system is not sustainable. In Europe, many people like free range, like eggs from free range farms, because they think it's better for the welfare of the animal. And for example, the situation in the Netherlands at the moment is that, well, our minister imposed a housing order mid-October of last year, and that is still in place, even though it's already June at this moment. So actually it means that this system of free-range farming is not possible anymore in the current situation. And on top of that, I think in Europe, tens of millions of poultry were killed in this year and the previous year, and also that is not compliant with sustainable farming practice if we want, to have also a sustainable way of farming. So that means that we need to come up with another solution, and I think, well, vaccination is of course the most logical one. And well, why are we not doing that at the moment? It's maybe related a lot to legislation, but I think also to the way it has been implemented to date. The vast majority of vaccination against highly pathogenic avian influenza has been applied to prevent disease and mortality and not infection, and that has resulted in those countries where it was implemented in silent spread. And I think, well, one of the reasons is, of course, that these countries that started using vaccination were also the countries that maybe had most difficulties with having a good veterinary infrastructure to cull or infected flocks or to compensate farmers. So they also did not have a serious other option like, the more developed or the higher income countries they do have. And that, of course, gives a bad name to vaccination, because it's associated with, preventing disease, but not preventing spread. So what should an ideal vaccination program do? It should, as indicated here, prevent infection when exposed. It should stop between farm spread when it is used as an emergency vaccination. So the first item is related to preventive vaccination, the second one more to an emergency vaccination, and a third option, what you also would like to do in case you want to prevent infection, is that in regions where the infection is enzootically present, it would eliminate the infection. And on top of that, of course, we also would not want to have adverse effects on production or other serious expenses due to vaccination, and it should not result in trade embargoes. So within epidemiologists, because I'm an epidemiologist, we use for these first three items, in particular the effect on transmission. We try to quantify that in order to establish the effect of vaccination. And for that, we use a measure of transmission that is called the basic reproduction ratio. And I think it has gained a lot of popularity during the COVID epidemic, because also there, I think the transmission of SARS-CoV-2 virus among humans was regularly expressed as the basic reproduction ratio, which gives the average number of secondary infections caused by an infected animal in a fully susceptible population. So that has been quantified also for highly pathogenic avian influenza virus and for low pathogenic avian influenza virus. And in that case, it is more or less, in the same order of magnitude. For highly pathogenic avian influenza, it is 2 to 10. And for for low pathogenic avian influenza virus, it is quantified at 4 to 15. So it can be well, quite variable depending on the situation where the chickens are housed, because I'll show in a few slides what is affecting that. So what does R in practice mean? In practice means it for in particular that it has a threshold at the value 1. So here you see a graph with, on the y-axis, the probability that a major outbreak will occur, and a major outbreak is an outbreak where a large proportion of the population will get infected. And on the x-axis, you see the value of the reproduction ratio, and you can see in this graph that it has a threshold at the point 1, meaning that if the value of the reproduction ratio is below 1, the population will be protected from infection, whereas if it's above 1, then the depending on the value of R, a larger part of the population will get infected. And that also means that the goal of a vaccination program is to have a reproduction ratio below 1. What does R mean? What determines R? So the reproduction ratio is determined by a number of biological items that I think most of you are familiar with. So the one is the infectivity of an infectious host, which is kind of related to the number of viruses shed by a host, but also the survival of the pathogen in the environment. Of course, the susceptibility of the contact hosts are important, in particular the immune status, how is it protected, how much virus is needed to infect the chicken, and also the duration of the infectiousness is important. This is also related to the immune status of the infectious host, the survival of the pathogen in the environment, and also, of course, also the case fatality. If you've seen the previous slide, you might have noticed that actually these values of the reproduction ratio of high path virus and low path virus, they're not that much difference. And the reason is, of course, you might have expected that the reproduction ratio would have been higher for high path virus, given that it transmits much more quickly. But for the reproduction ratio, that does not matter, because in this case, for high path viruses, these secondary infections, so these 2 to 10 infections, take place in only 1 or a few days, whereas in low path virus, these 4 to 15 infections, they might take place in 1 to up to even 2 weeks. So that means that despite these reproduction ratios being more or less the same, high path virus still transmits much more quickly, because the contact infections take place in a much shorter time interval. So the duration of the infectiousness is important, and the contact rate is important. So the population density, how the housing is important, whether it's cages or free range system, and of course the morbidity, as well, if chickens get sick, they also might not transmit it as quickly as if they are healthy. So how can R be quantified? We normally do that in transmission experiments, and a transmission experiment looks a bit like here. So we have chickens in a pen, we inoculate one or a few, we have non-infected chickens together with them, and then we just look in time what is happening, and we see, well, that contact infected chickens get infected, and even if they are infected and they recover, then they get immune. So that means in this way, and then also using some nasty mathematics, we can quantify the reproduction ratios. That has been done for several also examples in vaccination also, and then actually many of the examples as they are given here and described in literature, we've seen that vaccination is able to induce a reduced highly pathogenic avian influenza transmission to a level that this reproduction ratio is below 1 in experiments. well, already documented in 2005 by Jeanette van der Groot, a reproduction ratio close to 0, by later on in ducks as well, in chickens, later on also by more recent isolates of H5N1, also in Indonesia by Oktiputri and in Turkey. So this indicates that in principle, in a controlled situation, the vaccination can induce a sufficient level of immunity to stop transmission. But well, you all know, I think most of you are from practice, maybe much more than I am, is that of course transmission experiments, they are only well, a simplified representation of what happens under field circumstances, and they have a number of advantages, and the advantage is that they are controlled. So you really have a control of the situation, that vaccination is the only difference between your vaccinated group and your control group. You can standardize them, and also that also enables you to compare transmission experiments over time. Also makes that they are repeatable, but they also, of course, have a number of drawbacks, and that is that they are not completely representative for the field situation. And well, there's an issue with the animal experiments, but that's not relevant here. But this is more from a welfare point of view, that at least we need to reduce animal experimentation as much as possible. So that means that, well, from an experiment, we need to make next steps in order to make it more like the field situation, and that means that we try to mimic them more. We really would want to do experiments under field conditions and have not been able to do that yet. And well, in epidemiology, we also like to do mathematics. Starting with this first point, animals were vaccinated in the field and then exposed to the virus, and that gives a much more less favorable situation of these classical vaccines. So these are inactivated vaccines being used against the transmission of avian influenza virus. And then actually these experiments, they kind of point to the fact that for the inactivated vaccines, so the classical vaccines, to be effective in reducing transmission, you need an antibody titer that is at least 3 or higher, an hemagglutination inhibition titer that is at least 3 or higher, in order to protect these viruses from transmission. So if you obtain a titer HI exceeding 3 or higher, then and so an homologous titer, then you're able of to prevent this transmission. But well, and also another observation we did in the Netherlands, but also in Indonesia, that under field circumstances it's quite difficult to obtain them in a controllable way. And also there are really a number of publications by Oktiputri, Guskoch, Citaras that indicate that is really difficult to achieve in the older vaccines. And I think that's also why, at least well, in Europe, people have been reluctant to use vaccination because this would point to silent spread of the virus. The question we have is how effective are modern vaccines in reducing these transmissions? And at the moment we are in the process of testing them. This is a list, I think, that is really familiar to David Swain, a document that has been put on the website of the International Egg Commission. You can still find it, which indicates 11 points that need to be considered when applying a vaccination program. So one of it is related to preventing infection, prevent shedding upon infection, and this reproduction ratio below 1. But it also related to having high quality vaccines, and a number of the items that will occur in the presentation of Sjaak, like the Diva strategy. But one thing to stress here is that, well, vaccination in this sense, according to the people who drafted this document, is not a strategy to stand on its own. So it needs to be accompanied by a good surveillance strategy, but it also needs to be accompanied by a good biosecurity strategy, because, well, it is thought that the failures of vaccination, as they are have been observed in the field, are also related to the point that these vaccines have been used, and that was the only thing people did, not taking into account any other option anymore. And that is definitely not a good strategy to follow. So in conclusion, and this was my part of the presentation before I continue with Sjaak's part, due to enzootic infections of wild bird populations, stamping out infected farms is no longer effective to eliminate HPAI virus. No matter how many farms we depopulate, the virus is not going to go away anymore. To prevent circulation of a virus in poultry, vaccination should not only induce clinical protection, but also result in reduced virus transmission in the field. And to exclude silent spread of the virus, vaccination should be accompanied by an adequate surveillance and biosecurity. And then I continue with the presentation of Sjaak de Wit, and he will be able to follow up on that much better than I did. Sjaak started also with the reasons why it is needed to change the strategy. So he compares here the situation before 96 and from 96 on. So as we've seen, outbreaks were rare before 96 and are frequent now. They would affect a small area for a short period, and now they affect countries or even continents and have big endemic areas. The eradication was possible of highly pathogenic avian influenza virus before 96, and it's now only, you manage to do it locally and very often only for a part of the season, not completely anymore. We have this situation in wild birds, and also like it's indicated here in mammals. I think that's also something that we've seen in Europe now during the past two seasons, also more mammals, wild mammals getting infected, which might point at changing virus. Illness in humans as an item, what was rarely observed before 96, and at least in developing countries is noticed quite often now. The fact that at least in Europe, but I think also in other regions, there is an increased demand for free or organic farming, which does not comply with HPAI anymore. The understanding of the public, which is decreasing, because if you only can keep poultry by yearly killing millions and millions of chickens, what does it tell the general public about the sustainability of such a sector? Before 96, there were rarely trade problems because, of course, the affected areas were so minor, and now that it is more and longer giving trade problems. We have more vaccines available, as we will see in the presentation of Sjaak. The application is also getting different, and we are also capable of applying a Diva strategy, which actually means that we are capable of detecting infected birds in vaccinated populations. So here Sjaak, and I think David wants to do that as well, is advocating a symposium or a meeting to be held by the International Alliance for Biological Standardization on October 25 and 26 in Paris at the headquarters of the OIE. You can read here, you see David being the chair of the scientific committee. And this is a meeting on high pathogenic avian influenza vaccination strategies to prevent and control highly pathogenic avian influenza. And I think this part between the double dots is important, removing unnecessary barriers for usage. So that's really the emphasis here. It states that vaccination can be a useful tool for preventing and controlling avian influenza, but its use is prohibited or severely restricted in many countries worldwide, in particular also in Europe. Why the use of vaccination of avian influenza vaccines would increase the sustainability of poultry production, improve animal welfare, reduce economic damage, and reduce human infections, and also contribute to consumer and animal welfare acceptance of control programs. I think this is an important statement made there. Given in red here, a harmonized vaccination strategy with updated vaccine strains and innovative vaccine technologies combined with appropriate diagnostics, surveillance, and disease management can offer a better approach than the stepping out alone policy that is being applied now. But I think it's really also here stated clearly that it's not the vaccine alone. It's also the new technologies, but it needs to be combined with the appropriate diagnostics and surveillance and disease management, which includes the biosecurity as mentioned before. And I think a goal of this conference would also be that negative results of this surveillance strategy would mean a disease-free status. So which vaccines are there at the market at the moment? So I think it's clear to most of you probably that, well, in contrast to many other poultry vaccines, we have no live vaccines, although sometimes you might read about it in literature. I think nobody thinks this is a wise idea, because if we release a live AIV vaccines that is, well, still capable of spreading, then, well, we run the risk that this vaccine virus will recombinate with circulating low-path viruses, and then our cure might be worse than or a solution might be worse than the cure we are trying to control. So this is not considered safe. And that means that in the past, it has been mostly inactivated vaccines, the classical vaccines, which have a complete virus that is killed. So they are safe, non-replicating, but of course, a drawback is that they only induce an antibody response, which of course it's limiting for the induced immune response. Same is a bit for the subunit vaccines, which will be the vaccines based on one protein of the virus, the hemagglutinin protein. They're also safe, non-replicating, but they also will only induce the antibody response. And then the focus at the moment is more at the more novel vaccines, although they're also already on the market for quite some time. The live vector vaccines, which are available in quite a number of manifestations. Like you mentioned here, the herpes virus turkey vaccine, which is maybe the one most widely used. The fowlpox vaccine, which has been used, I think, quite a lot in Mexico, for example. Newcastle disease vaccine, which also well, is already, at least in the literature, described quite a lot. I don't know whether it has been used in the field a lot, and the reason for that is that, of course, many people vaccinate against Newcastle disease, and that is not very easy to do together with an avian influenza insert, because your maternal derived immunity might not make this virus replicate sufficiently. ILT vaccine, adeno vaccine, salmonella vaccine, duck enteritis vaccine, which is in particular being used in ducks because the herpes virus turkey vaccine does not replicate in ducks sufficiently. So in ducks you need a different vaccine. And all these vaccines, they are built on the fact that they're quite large vector viruses which have the hemagglutinin of avian influenza built in it. So in that case, they're kind of genetically engineered vaccines. The vector gives them the advantage that these vectors replicate. So besides antibody induction, you also have a T-cell response in these induced by these viruses, which gives them a better protection. So I think these are the ones that are at least at current most promising. And in addition to that, there are novel vaccines. I think there are also, for example, novel subunit vaccines based on the protein, which certain manufacturers are being made. But From the COVIDs, we also know the mRNA vaccines, which are also being developed for hemagglutinin, mRNA of influenza, and also DNA vaccines have been described already for quite some while. Need to speed up a little bit. So these vaccines need to be combined by what we call a Diva strategy, and a Diva means differentiating infected from vaccinated animals. So the field infections must still be detectable in the flocks despite the flock being vaccinated, which used not to be possible with the inactivated vaccines, or at least difficult, given that you never would know what the next virus would be. Where with these novel vaccines, it is possible, and you can do that by trying to detect antibodies that are induced by the field virus, but not by the vaccine virus, just because it's only based on hemagglutinin, for example. So you can use any other protein to detect antibodies. But also, of course, you can try to detect the field strain itself, for example, by an RT-PCR. Because if you have a non-replicating vaccine, it will just not be detectable if it's a killed vaccine. And if you have a replicating vaccine, if your target is another gene, for example, the M gene instead of the hemagglutinin, you can also easily detect it. So there are ample opportunities now to have a good surveillance strategy combined with a vaccine, with vaccination. So we're really capable of detecting silent spread in vaccinated flocks. Some examples Jacques presented here. So in the past, it would be oil emulsion vaccines of complete virus. Now these oil emulsion vaccines are still capable, or are still on the market, just as subunit vaccines, which do not replicate and only induce an antibody response. And we have these live vector vaccines and the RNA particles, which replicates and give an antibody and a T cell response. And for the tests, we have the traditional tests that can be used for many of these novel vaccines, but also now the newer techniques like the RT-PCR, which you can hardly call new anymore, and also a kind of sequencing and on-site tests that can be used. Just an example of a vaccine Jacques gives here for H5 vaccination based on the herpesvirus turkey vaccine, and given the authors, which include Jacques here, but also Yannick Gardin, this will be the Diva vaccine, which has a strategy of being administered first on day 0. This herpesvirus, so it can be either administered in ovo or just after hatch. And then, of course, during the the idea of these herpesvirus turkey vaccines, as you're probably aware of, is that these herpesvirus virus keeps on replicating during the life of the chick, just because it's this is what herpesviruses do. And also that means that there will be a constant release of H5 and in that case a constant trigger to the immune system. But still, this could be combined with a vaccination during the rearing periods, in this case of a subunit vaccine or an RNA particle. And then you have different possibilities to do a Diva strategy in a flock that has been vaccinated in this way, by either looking at a nucleoprotein antibody, so not being H5. You can use any other antibody for that. Given that you find any of these other antibodies besides H5 will mean that you have had a field infection. And of course, you could also test for real-time with real-time PCR for the virus, but that's of course more work, and you need to have better luck, given that antibodies give you the cumulative incidence of the infection. Some other examples. Do you want to comment on this, Jacques? Just to give you also some interaction. if not, maybe Jacques has. So again here the hatchery at day 0 or in ovo, it could be a system with this hatchery vaccination followed by a fallpox H5 vector on day 8 in a wingweb methods. Also a booster could be an H5 subunit at week 14. Well, it could even be at week 8 and week 14 if that is needed, but I'm sure Jacques could comment on that. And well, each of these systems can be combined with a Diva strategy based on Diva monitoring in these AI vaccinated flocks, given that they only have been exposed to the HA of H5 in this case, and not to any other of the proteins of the avian influenza virus. So again, we come here to this commercial break of Jacques de Wit regarding this vaccination meeting, which is, I think, very important, because I think it's really important that in October, many of the people related to FAO, to OIE, and yeah, I'm sure many government officials will be there to discuss this item in order to change the policy we are in. And I also hope at that time that we will have some additional information regarding the effectiveness of these new vaccines on transmission. Having said that, well, I thank you for your attention. I well, really need to apologize that I, of course, did not do the part on Jacques' behalf as good as as he would have done himself. But I still hope that it was useful to you, and I really hope that Jacques will be able to help to answer the questions that you might have.
Yes. Apology for letting you alone, Arjan. I was talking, but I was still muted. So sorry, it took me some time to solve that. So okay. Thank you.
Thank you very much, Professor Stegman, for giving both lectures. I will give time for questions or any other comment if you wish. There is one question from Dr. Ehud Shachar. How these vaccines cope with changes in the viruses, and what is the cross-recognition and protection against new emerging variants?
Yeah, so I think that's a good question, because it's something that well, receives a lot of attention. So if you just look at these killed vaccines, then it's quite clear. So you need to have these titers of HI3 or higher to the homologous virus. So that also means that it's crucial that you use a good HI test to test that, because the antigen in your HI test must really be well, similar to the antigen in the field virus that you're trying to protect your chicks against. So in that case, it needs to be a homologous system, and there is well, a kind of a system developed, which is called antigenic cartography, which could also in vitro kind of well, make an estimate on whether this vaccine is still protecting good enough against this system. It has been developed for humans quite well, and well, there's also some experience with it in poultry. For the novel vaccines, it's, I think, more complicated, and because it's more complicated, I give the word to Jacques so he can help me out here.
So it's like you mentioned, and we all know, even influenza is a moving target. So there will always be mutations, there will always be some changes in antigenicity. So therefore, we are going to need vaccination programs which hopefully provide a broader protection than what the inactivated vaccines on their own can do. And for that, the replicating vaccines are not only inducing antibodies, but also inducing T-cell responses. And we still have a lot to learn, but we have a quite good indication that these T-cell responses make the protection broader than just the vaccines that induce antibodies. So therefore, I had this slide included, and apology, Arjan, again, I was not able to respond at the time, but I guess we all realize that a single vaccination and that it would protect then the bird up to 80, 90 weeks of age. I think that would be a theoretical dream. That's not going to happen. Very likely we will have to use maybe several live vaccines and boosting by a subunit, for example. So these are just some examples, maybe based on the field pressure in the country, or maybe in a certain compartment of your industry, that you might, well, maybe one vaccination, a certain vaccine might be sufficient. For other ones, you have to use, well, maybe a H3 vaccine, and then maybe, let's say, HVT. Then maybe at 8 weeks, you can boost with another replicating vaccine, fowlpox, and then a good subunit vaccine, maybe with several H5 antigens. And then hopefully we might achieve a much broader protection than, or at least a broader protection than with the single vaccines. And hopefully that will be sufficient. But therefore we have this, that's what's very mentioned several times, the monitoring, the surveillance, checking with right antigens to, people always have to keep alert for changes. Is it sufficient? Hopefully it will be. If not, we have a problem.
Okay. Other questions?
Yes, I have one, not if it's all right.
Yes, please.
I'm just wondering, I'm more interested in the, not only on the pros, but mostly on the cons of this, how to say, non-conformist view in relating to AI and vaccination. And I wonder if we have any practical experience from countries that have already taken this step, like China, if it works at all. I mean, in a large scale, not in a trial, in a field or in whatever. Do we have any solid data from countries like China suggesting it fails or if it approves?
Well, I guess, but there's a very nice example of Italy and Hong Kong, which have applied even with the old-fashioned, only inactivated vaccines. They did a good job because they had a very strong guidance. They did the monitoring, still the culling of infected flocks, and they resolved the problem. So we see with countries, for example, in Egypt, but I'm sure you will have a lot of information about it yourself, that with the use of combinations of vaccines, replicating vaccine and then boosted with subunits, they tell us the results are much better. However, the data are not really available. Whether there was a good monitoring and surveillance, we do not really know. And therefore, like Arjan already mentioned in the beginning, we are going to test this kind of vaccines for ourselves to see, how strong are the cons and how good are the pros. Separate the theory from reality. But I would say, on the other hand, do you have another solution than just keep on culling a lot of flocks? That's the other part. So
yeah,
you have to make a step forward.
One thing to add to that, and I think that was also what we said in the call to Hendrik Genetics and other of these breeding companies, we would be very glad to receive at least data from companies that are working in these fields, just to try to estimate that, because I think in the combination of biosecurity, vaccination, and surveillance, we think it should be possible, but we would need data to corroborate that, and that is just not available anymore. One thing to add for China, because you rightfully mentioned that it's used quite a lot there. I have not seen good data on the animals there, but on the other hand, they have shown, I think, quite a considerable effect of vaccination on the infections in humans. But perhaps if David is in the call, David, could you comment on it?
Yeah, I just want to say thank you, Aaron and Jacques, for a really good seminar. I think you covered all the points very, very well. just a few additions to what you've already said back to the last question. There are, of course, criticisms out there for vaccination. I think most of those criticisms can be easily answered, addressed, and corrected by a correct surveillance program. And that, I think, is where many of the countries who are doing vaccination, they tend to go all in with the vaccination and back off on the other parts of the control program, including the surveillance part. So they implement a vaccination program. They basically quit looking for the virus. They also quit depopulation of infected flocks. And so that creates a problem where you vaccinate, you don't know what's going on. And I think, if we were going to use vaccination, which is not approved in the US yet, we would make sure we had to maintain our existing surveillance program. That's a real critical part of it. Because one of the criticisms that you hear quite commonly about vaccination is, oh, you get a silent infection. And I think here is where the field data would suggest that silent infections are much less common than we can produce in the laboratory with our experiments. Because in our experiments, we do a challenge of an extremely high challenge dose. And many times the vaccine does not match the field virus. And yes, we can produce silent infections. But in the field, the exposure dose varies greatly. So most of the time, the exposure dose is not that high, and the vaccination itself works much better. I already mentioned about the decrease in human cases. That's one thing that has been very well shown across many countries that implement vaccination programs. Pre-vaccination, they had very high levels of human infections. After vaccination, they decreased tremendously. In the same way with animal outbreaks, is that once they implement a vaccination, the number of outbreaks in the agricultural sector greatly decreased, and the food security of the population greatly increased. So those are real positive things, but we have to manage the expectations about making sure we do the surveillance. As Jacques had said, the surveillance is really critical part of that. And I'm a strong believer in looking for the virus in vaccinated flocks. That needs to be an ongoing process using real-time PCR, because it's the virus spreading that's the big issue that Arin had already shown when talking about the reproductive factors and the numbers involved in that. And you want to get those numbers down so you stop that transmission. And the only way you can really assess that is to do surveillance, really survey. The last thing I'll mention, and it's about vaccination, the types of vaccines you use. And there's quite a bit of experience in Mexico, which has been vaccinating since 1994 for H5 and since 2012 with H7. There's also experience in Asian countries, as mentioned, China, Vietnam, et cetera. And I think some of the things that have come out that is very understandable. For example, in Mexico, they commonly, in some of the broiler companies, use a fowlpox recombinant as a primer. And that actually has to be given in the hatchery, and it works good as a priming dose. But then they also follow that up with vaccinations in the field with killed vaccine. The low cost of labor in Mexico allows them to use killed vaccine in the field. In broilers. So, but also HVT at day of age is also widely used. When you start looking at booster vaccinations, almost all the booster vaccinations are with whole kill virus or a hemagglutinin-based inactivated vaccine. There is one baculovirus produced vaccine that's used heavily in Mexico as a boosting vaccination, although the killed whole viruses are by far the most commonly used vaccines. The Newcastle vector is licensed and used in Mexico and China. The problem with that, as already has been stated by Arin, is that if you have a Newcastle vaccination program, that severely inhibits the ability of that vaccine to give you a boost unless you know the titers of the birds. And you really, in our experimental studies, you have to have a titer which you can't find for Newcastle to get a boost to happen. So usually Newcastle viruses as a vector are not really good for boosting in most places in the world. And fowlpox is the same way, is that in most places in the world where you do vaccinate for fowlpox, you can't use it as a booster, or if you have a heavy burden in the field of fowlpox, you can't use it as a booster either. So you have to really know the flock. That's where the veterinarian comes in. Know the flock, know what you have in that flock as far as other pathogens or other vaccines, because the selection choice for your influenza booster is going to be greatly impacted by that. In the US, we do have several products that have gone through the licensing process, but we currently have not approved them for use in the field. So we're still going through the same process the European Union is reassessing vaccine. Can it be used in the future? And I think by far the biggest issue is trade ramifications. And we have not been able at this point to have frank discussions with trade partners and let them know, hey, vaccine would really help everybody around the world and especially improve animal welfare. Thanks.
There's a question by Dr. Crispin. What about prospect of the virus becoming endemic if we stop depopulating? Professor Stegman?
Yeah, I think it relates to the discussion we were having until now. So if we stop depopulating and we would not do anything, I think, well, the prospects of the virus becoming endemic are really, really high. So the only alternative to depopulating like we're doing now is this combination of vaccination, good Diva surveillance, and still also attention to biosecurity. So this combination of three should make the situation more sustainable.
Okay. Other questions? There is a question, but I think he didn't finish to write it down. What is the probability that vaccine will induce new vaccine escaper strains?
Yeah, so in that case, well, the vaccines will certainly put pressure on the system, but also for that, if we have a vaccine which is capable of this, of reducing this reproduction ratio below 1, you will stop the transmission, and that's also the best way of preventing these escape mutants from happening. You get these escape mutants if you're actually having insufficient immunity, because then of course you will have much more virus replication, so much more pressure on the vaccines. But maybe Jacques, you can also comment on that.
No, you're exactly right. And because you have to combine vaccination with a good surveillance system, you will pick up these, you will find these potential, well, these mutants, and you have to kill the flock. So these viruses will not spread because you kill the flock. So that's why the monitoring and surveillance with the Diva strategy is so important. It's a vital part of vaccination.
Yeah, but a good point as well is in this question is also that, well, of course, for viruses like influenza, like we've seen for the corona, of course, well, they will keep on changing. So in that sense, if at the end you have a vaccination platform which can be easily adapted, it's much preferable, I think. And in that sense, for example, if I look at the Netherlands, I don't know whether it's across Europe, it's always remarkable that while taking these changed mutants in the vaccine seems to be much more complex than in human vaccines, where you can change it apparently each winter.
And by the way,
I think, sorry.
There will be mutants anyway. The wild birds will bring you new ones every year. So.
If I may add, it was mentioned also by Professor Stegman that using vaccines is you can not just having an entry point, but also having an exit point, exactly based on surveillance, based on risk analysis, and then knowing exactly when to vaccinate, which where and which poultry to vaccinate exactly, and when to go and when to exit also. So using vaccine not as a world program in all the country, but using it as an aid to in very high risk places, as we have in South France, for example. And I think that years ago it was also used in Italy. In certain areas, they use vaccines to control cases of avian influenza with high surveillance and also entry and exit points. So this is a very important issue also to mention. Another thing is as vaccine producers, I think there's no requirements in the pharmacopoeia yet regarding inactivated vaccines, and also it's a need if we will want to produce vaccines, also to have scientific and professional requirements in the European Pharmacopoeia regarding vaccines. Also in the US, the exact requirements needed for vaccine production. Any other questions? Professor Swain, can you add something regarding the current situation in the US right now, please?
Yeah, just a brief update. The epidemiologic curve in the US is now on the declining side. We only had one case in the past week, one commercial flock. The week before, we had a couple of flocks, backyard and a commercial. And so for us, the commercial flocks have greatly decreased in the last month, and we're down to just a few scattered flocks that are showing up out west. We haven't had any new flocks in the eastern part of the country for a couple, 3 weeks. I think you already mentioned earlier, Natty, that we are at a little close, pretty close to 38 million birds that have been depopulated, 36 states. I think we're 361 premises, and that actually is both backyard flocks and commercial flocks. The backyard flocks, this outbreak compared to 2014-15 is much higher proportion of the premises than it was in 2014-15. 2014-15, we run about 10% of our premises that were positive were backyard. This time it's running about 45% of our positive premises are backyard flocks. And the other thing that's changed quite greatly this time around is that the number of wild bird cases are much higher. 2014-15, we had 75 confirmed wild bird cases. This time we're over 1,200 wild bird cases. So there's a lot more, which appears a lot more virus in the environment, wider spread infection of wild birds across all 4 of our wild bird flyways. And because of that, at least in our preliminary analysis, it looks like most of our cases, the vast majority are primary introductions from the wild bird reservoir, and a smaller number of those are lateral transmission.
Thank you. 2 other questions, one from Dr. Dana Goldenberg. How can you design a Diva test in a situation where a killed vaccine is given in addition to a subunit vaccine? Maybe it's for Professor DeWitt.
I'm not sure if I understand the question. Is it about use of...
How can you design a Diva test in a situation where a killed vaccine is given in addition to a subunit vaccine?
Okay. So if a whole virus inactivated vaccine is used, then Diva serology is, well, you could use sentinels, but let's say that's not going to be very practical. If you want to use a Diva strategy of the use of inactivated vaccines, I guess the RT-PCR is very suitable, but it's more complicated in this kind of situation than when you are able to avoid inactivated whole virus vaccines.
Thank you. Another question, can ELISA test detect highly pathogenic avian influenza?
Well, I guess it's the antibodies against high-powered influenza. Let's say in unvaccinated birds, high-powered will usually kill the bird before there are antibodies. But if you have a vaccinated bird, Diva with the subunit vaccines or whatever, and then they get infected by half-off, the ELISA will be very, very well able to detect the antibodies without any problem.
Thank you. Other questions? No more, okay. So again, I would like to thank Professor Stegman, Professor DeWitt, Professor Swain, David Swain from the US, for taking part in this Zoom conference. For all participants, I hope we contributed to to your knowledge, answer some questions on early pathogenic avian influenza vaccination, and most of all, provoked you out of the box thinking. I wish you all the very best, and thank you again for participating. Thank you again, and if no more questions, I'm closing this meeting. Thank you all.
Bye-bye.
Bye.
Bye-bye.
Thank you.